Well, hello. In this video, we are going to start to learn the basics of robot kinematics. So in order to do that, we will have to talk about points and vectors. We will talk about Cartesian coordinate systems. We will introduce a new way of describing coordinate changes. This will lead us to the presentation of homogeneous transforms. And then finally we are going to shift to MATLAB and make some examples of use of the robotics toolbox. So in order to start and to orientate a little bit where are we heading in these concepts, using these concepts, we will propose some mouth-opening questions. So for that, I suggest to take a quick look at this robot that we have on the right, which is an ABB industrial manipulator, which is a machine that is present in many factories all over the world. So without knowing anything, we should make a mental effort and try to figure out how many joints are there. Okay, moving joints. Well, a joint is some part of a robot that can rotate or can be displaced, right? So this idea is easily understood by thinking about the joints of the human body. Some of them are the elbow, the wrist, the neck, the knee. They all are joints that we can bend, twist, in order to attain different positions. Now there's an important part of this course which is about choosing the right value of the joints of a robot, and this starts by knowing how many joints are there. Okay, so by looking at the lower part of the robot, it really stands out that there is a rotation around a vertical axis, and this accounts for a first joint. Then there's a second joint around an horizontal axis, and here there's a third joint again around an horizontal axis, which is parallel to the previous, right? And then finally there are three joints around the wrist of the robot. The hand of the robot is any tool that is installed at the end of the robot and is normally adapted to the specific application of the robot. So we have counted 6 joints in this robot. But this comes at no surprise, as the joints of the robot are used to place the hand of the robot, the end effector of the robot, in space. This means that if I need 6 degrees of freedom to place a solid body freely in the world, 6 degrees of freedom which are distributed in 3 linear motions and 3 rotations. Okay, so in order to place a solid in the world, I need to fix 6 numbers, 6 degrees of freedom, and that is the reason why we use 6 joints in the robot. So the second question, how do we represent the position of the hand of the robot? Well, the hand of the robot is a solid and it requires 6 degrees of freedom. Then there's a question that says, with respect to what coordinate frame? Okay, so if I use some coordinates to say or to state or to determine the position of the hand of the robot, these coordinates should be referred to some coordinate frame. Okay, so whenever there is a robot application, there should be a coordinate frame outside the robot to which we should refer the position of the hand. Okay, Now, if we have a coordinate frame, how do we express the position of the hand mathematically? Well, this is a reference to physics. This is a reference that should lead us to think of translations and rotations. There are 3 translations and 3 rotations that, if they are properly defined, they determine the position of a solid body in a 3D space. But the interesting thing is that now that we have placed the hand of the robot in space, does it depend on the values of the angles of each of the joints that we have described? Yes, there is a relation between the coordinates that describe the position of the hand with respect to the coordinates of the angles of each of the joints of the robot. Okay, so this is just talking, but we will get there by doing mathematics. Well, okay, this slide, it goes very quickly, okay? I'm just saying that a point in space is okay, a non-material, a zero-size location on the plane, and it is represented by a uppercase letter like capital P here, and it corresponds to a couple of coordinates, which are the distance to the origin of coordinates in each of the axis directions. Now, associated to a point, there is the concept of vector, which is quite like the same, but not exactly, okay? A point is just a location. A vector is an arrow that joins 2 points. The first point is the origin of the coordinate frame, and the second point is some location in space P. So we can identify a point in space in 2 ways: just as a point with its 2 coordinates, as we saw before, or as the vector that joins the origin of the reference frame with that point. In any of both cases, the coordinates will be the same, A and B. But in the case of a vector, we will use the lower p or lowercase letter to identify the vector. So, how about coordinate frames? We have seen that in order to describe the position of a point, we need a pair of axes. Well, okay, so a coordinate frame in 2D is a base for referencing points on vectors. So, our reference frame is just a couple of arrows, directions that cross at a given point called the origin. So, in general, we use the labels X and Y in order to name those arrows, and we have to consider some particular orientation of those axes. Okay, in general they should be perpendicular, but there are 2 possibilities: right-handed coordinate frames, that like the one that we are depicting here, or left-handed coordinate frames like the one depicted down here. Okay, what is the difference in words? Okay, in the right-handed coordinate frame, when we turn from the x-axis to y, the shortest path, we are turning a positive angle. The left-handed coordinate frame, turning from x to y through the shortest path, gives us a negative angle. Okay, that's the difference. Well, there's a quick exercise. Which of these are right-handed? Which of these are left-handed? Okay, it is clear. The A coordinate frame is left-handed because there's a negative angle that goes from x to y. B is a right-handed coordinate frame, and C is a left-handed coordinate frame. So we have discovered what is the position of a point with respect to a coordinate frame. How do we position a body with respect to a coordinate frame? Okay, well, first of all, we have to describe what is a body. Okay, well, we need a body here in order to describe a robot. Okay, let's think of a robot as a rigid body. In order to say exactly and completely where a body is located with respect to a coordinate frame in 2D, we have to think of that body as a set of mass points. Okay, so now let's make a closer look at this image and specifically at this red coordinate frame. Okay, think of the robot as a set of points, okay, a very large set of points which describes each of the material elements of the robot. Okay, so that's why we see these 4 points in here. So because the points form a rigid body, they have the property of having the same distance among them, and that distance will not change along time. Okay, and the subsequent property is that there is a coordinate frame attached to the rigid body, that is to the robot, to which the coordinates of every point mass of the robot will never change. Okay, so let's say that again. There is a coordinate frame attached to the robot to which the coordinates of each point mass of the robot will never change, will remain constant. Okay, so that coordinate frame is represented here by xb and yb. And now stating the location of the robot is just stating the location of the coordinate frame xb and yb with respect to y. And well, I will not really stop in here. I will very quickly jump to this slide. Okay, it's very, very easy. So in order to determine what is the position of these two toy robots with respect to an external coordinate frame xy, like the yellow one that we are seeing here, we observe that in order to move the yellow coordinate frame to fit it exactly with the green robot frame, we have to displace the origin of the xy coordinate frame to the origin of the green coordinate frame. Okay, so first we have to move the origins so that they stick together at the same point. And in order to do that, we need two coordinates. That is the horizontal displacement and the vertical displacement of the origin of the yellow frame. But once we have reached there, then we have to make a turn, okay, an angular turn, so that the directions of the axis of the yellow frame match the direction of the axis of the green frame. Okay, so in general we have made 3 operations with a number associated to them to get from the yellow frame to the green frame. Okay, so if we write down those 3 numbers, then we are in a way giving the coordinates of the green robot. And the same happens with the red robot. Okay, in order to displace or to move the yellow frame to the red frame, which represents the red robot, we have to first displace the origin of the yellow frame so that it matches the origin of the red frame, and then we have to make a twist. These motions are described by the xy coordinates of the motion of the origin of the yellow frame and the theta angle that we have to turn the yellow frame in order to match the directions of the red frame. So, what is a pose? Okay, so with this in mind, we define the pose of a robot as the complete set of coordinates to locate a robot in the 2D space or 3D space, but we're now in the 2D space. And this represents the position of the robot, okay, which would represent the origin, plus the orientation, okay, the total coordinates to say what the robot is. So in these 2D examples, and where the robot doesn't have any joints, by the way, The pose is defined by three numbers, the x, y, and theta numbers that represent the translations and rotations that we have to perform on the yellow frame to get to the robot coordinate frame. Okay, so the pose is the set of these three coordinates. Now we are going to use a new notation which is represented by this expression PA. What does it mean, PA? P left super index A is the coordinates of a vector expressed in reference frame A. Okay, so now the second expression represents just the coordinates of some vector P in reference frame B. Reference frames A and B are just, it applies to each differently to each example. Just think of just two reference frames and observe that the coordinates of the vector that goes to point P are different if they are referred to frame B or if they are referred to frame P. Now, what we are searching for is a way to change coordinates. That is, if you know the coordinates of P with respect to B, then there should be some way to change coordinates from B to A and obtain the coordinates of the vector that goes to the same point in reference frame A. Okay? So how do we change from this red arrow to this blue arrow? Okay? First of all, why do we need to do that? Well, okay, PB is something very simple to compute. Why? Because PB in our robot setup is a point inside the robot. And if the robot is a pure rigid body, then P has constant coordinates, so it doesn't change. It's a given data at the beginning of the problem. But as the robot moves in space with time, the coordinates of that point of the robot, which are constant with respect to reference frame, will change with respect to reference frame A, okay? And in reality, what we are interested in is the positions of the points of the robots with respect to the world, okay, with respect to the outside reference frames. So in robot applications, we need the PA coordinates. So in general, there's some mathematical transformations from PB to PA, which is, okay, we will see if there is a possibility of moving from PB to PA by pre-multiplying the coordinates of PB and then obtaining those of PA. And in order to do that, we will first define the framework in which we are working. Well, again, there's a blue frame, which is the world coordinates, and a red frame, which are supposedly the robot coordinates, the robot frame. And there's a point PB, and we have to transform from PB to PA. Let us define the three coordinates that define the location of the reference system B with respect to the reference system A. And as we introduced before, in order to define that relative locations between reference frames, we have to write down the numbers that will displace reference frame A to the location of reference frame B. It is clear that in order to get there, we must displace first the origin of the A frame to the origin of the B frame, and that happens along the T vector, which has coordinates X and Y. Okay, these are just numbers. Okay, I won't put again a superindex there. And once we have translated the A frame into the B frame, it is clear that we have to rotate the A frame along the theta, this theta, yeah, along this theta angle, this positive theta angle, so that the directions of the axis of the A and the B frame are matched together. So the pose of B with respect to A is T, that is X, Y, and theta. And using that information, we will transform from PB to PA. Well, in order to do that, we will use this particular projection. Well, first of all, I have to make a small amendment to this drawing, which actually comes from the Peter Cork book, and it has a slight error. Okay, observe that it is important to see that this B, this IB, and this XB is actually IV and XV. Okay, sorry about that. I'll just have to reframe, retouch this picture. But I mean, excuse me for not stopping the video from doing that. So this is the projection that we are going to compute. So first thing you have to keep in mind is that in order to translate from PB to PA, we will make an intermediate step. And this intermediate step is to translate from PB to, from reference frame B to reference frame V, right? And what is reference frame V? Reference frame V is a reference frame parallel to A, but with the same origin as B. And that's where this XV and YV appear, okay? So isn't it clear now that the blue reference frame is parallel to the A frame, but with the same origin as B? Okay, so the V reference frame is an intermediate reference frame that we will use for our computations. And now we will project the P vector from which we have the B coordinates into the V frame. And it is clear that these projections from this geometry, okay, follow a specific trigonometric translation. In order to do that, you have to make a small imagination effort. First, imagine that the point P is exactly on the XB axis, okay? So you have to imagine that IB is 0. If we are in the XB axis, then the projection at the V axis would be exactly XB cosinus of theta. On the other hand, now if we assume that the point moves to the I axis of the B frame, then we will observe that the projection along the XV axis is minus IB sinus of theta. Okay, so IB multiplied by the minus sinus of theta. Okay, this is just triangle formation. Well, now as the real P point has neither XB nor YB coordinates 0, the projection of the XV axis will be the sum of these two values, okay? And this is what leads us to the expression given by, try to analyze the first row of these equations. XV equals cosinus of theta multiplied by XB minus sinus theta YB. If we make now the same decomposition of the projections of the P vector along the IV axis, we will obtain the second row of these equations. Okay, we will not stop that. Okay, we'll leave that as an exercise, and then we obtain these expressions. The coordinates in the intermediate V frame is equal to this matrix cosinus theta minus sinus theta cosinus theta multiplied by the coordinates in the B frame. Well, this matrix that we have in here is what we call a rotation matrix. The rotation matrix can also be written as an R, and with a sub-index on the right called B, which is the origin coordinate frame, and a superindex on the left superindex V, which represents the destination coordinate frame. So when we move coordinates from B to V, we have to multiply those coordinates by this rotation matrix VRB. Okay, the rotation matrix has two important properties. The norm of the columns are all 1. It is easy to compute by applying the formula cosine squared plus sinus squared equals 1. And also the product of the different columns of this rotation matrix are 0. This means that the matrix is orthonormal. An orthonormal matrix will have the following properties that are presented here. The norm of the vector on the right of the matrix is the same as the norm of the vector that results from the multiplication, okay? So the change of coordinates from B to V does not change the norm of the vector that whose coordinates are changing, okay? This is because there is only a rotation between B and B. There is no translation, okay? So a pure rotation will change coordinates in a way that the norm of the vector is natural. And there's another interesting thing is that the inverse of the rotation matrix is equal to the transpose of that matrix. This simplifies the computation. For example, the inverse of this expression is just the result of changing the sinus, the sign of the sinus in this expression. But it is natural because the inverse operation is just a negative rotation. Okay, so it's the same result as making theta negative, and making theta negative just changes the sign of the sinuses, because the cosinuses are even functions, and the sign of the changing sign of theta does not affect the result. So if we have this way of changing coordinates from B to V, it is clear that the other way around, that is changing coordinates from V to B, is obtained by computing the inverse of the matrix that we have just computed. So this is the transformation from V to B. But this is equal, as we have said before, the transpose of the matrix VRB, okay? And as a matter of fact, a matrix changing coordinates from V to B should be named the same way, using the same convention, that is, putting on the right sub-index the origin frame from the coordinate change, and on the upper left left index superindex the destination of the coordinate change. So the transpose and the inverse of VRB is BRV, right? Okay, well. And now let's go back to the general framework, okay? So we are looking for a coordinate change from B frame to frame. And in reality, A frame does not have the same origin as B, so we have just made a partial coordinate change. We have to complete it by adding to the coordinates expressed in the V frame the x, y coordinates of the t vector. Okay, so now this is we have the v coordinates that we have just obtained by rotating the coordinates in the b frame, and then if we add to them x and y, then we will have the coordinates in the world reference frame. Okay, and this is developed using the result that we had previously. Okay, xv and yv are only intermediate coordinates, but the original coordinates are the b1. So the whole expression is composed of the rotation matrix multiplied by the xb, ib coordinates plus xy. And that is how we transform from B to A. But there's another way of writing this matrix expression, which is much more convenient because there's no addition anymore, and there's just a matrix multiplication, okay? So the initial expression can also be written as here. You just have to check and develop the first and second row of those equations to come out to the conclusion that they are equal. And now, what if we add a row, a third row below that just states 0, 0, 1? What will be the effect? It will generate a third coordinate with a 1 here, which is the same as here. So if we add a third row just full of zeros, we will get this expression, which is a much more compact form than we had before, okay? So if we express the coordinates in B as xb, yb, and a 1, which is a fixed third coordinate, and if we multiply it by the matrix that has on the top left 2 by 2 square matrix, the rotation matrix from B to V. And then at the right we have the t vector, which is the displacement of the origin from A to B. And then in the lower row, just 0, 0, 1. Okay, if we multiply this vector, this B frame vector by this matrix, then we will have this A frame vector composed by the XA, YA, and 1. Okay, this particular form of expressing coordinates with a 1 in the end is called homogeneous coordinates, okay? And the idea of calling them homogeneous is just a convention that highlights the fact that there is a homogeneous way of transforming between reference frame, okay? We only have to make one operation, which is matrix multiplication. We don't have to multiply and then add. All the operation is homogeneous. And the last and the nice thing of this is that coordinate changes can be operated in succession, one after the other. So if we think of the robot as a kinematic change with a chain of reference frame, we can change in sequence from one to the next, to the next, and to the next by pre-multiplying the coordinates by one matrix, and then the other, and then the other, and then the other, okay? And this is exactly what we were searching for when we added the 0, 0, 1 at the bottom of this matrix, to have square matrix that will produce every time coordinates in a homogeneous form. I hope this discussion is not excessively complicated. So the concept of homogeneous transformation arises from here, okay? So what is an homogeneous transformation? The definition is, it is the matrix that represents both a translation and a rotation that leaves us from A to B. So, in particular, if we have a couple of frames A and B, and if we assume that to get from A to B, you make first, and this is important, first a translation XY, and second a rotation theta to get to B, then the matrix that transforms the coordinates of a point in B into coordinates of A is the matrix that we have here. Cosinus theta minus sinus theta x, sinus theta cosinus theta y, 0, 0, 1. Okay? And this is probably the slide where you have to go back in the future, okay? Because there's a lot of confusion if you don't follow strictly this definition, okay? So the x, the y, and the theta has to be defined as the displacement that I have to do to get from the origin of A to the origin of B, and theta, the angle that you have to turn to from this second reference frame to get to B. For example, you might have all the other ways of describing the pose of B with respect to A. For example, you could say that theta is the angle that you have to first turn A, and then T is the displacement that you use to get to B. Okay, that's a correct definition. But if you define X, Y, and theta as such, then this will not be the matrix that transforms coordinates from B to A. And there is also a source of confusion because you define X, Y, and theta in the sense of going from A to B. But as a matter of fact, once you build the matrix has exactly the opposite sense, okay? It means transforming from B to A. Keep that in mind, please. There's a red sign in here, remembering that the matrix is built using geometrical steps forward from A to B, but the coordinate transformation done by the homogeneous transform matrix is backwards from B to A. Okay, and this leads us to the following topic, which is coordinate change composition. Well, I'll stop this video because it has been running for long. I will continue in the next one.